This is topic 4 in Unit 2, the multiplication rule with complements. So far this unit, we have only been able to find probabilities that were all or nothing. So for example, we flipped a coin and we found the probability that they all landed on heads. We had a 5-question multiple choice test where you randomly guessed and you got the probability that you got all of the questions correct. Or you had 4 tires and you selected 4 and you wanted the probability that none of them were defective. So this is kind of a problem because there are many cases where what if we want to know the probability where at least 1 tire was defective? What if we want to know the probability that we get at least 4 questions right to pass our quiz? So one thing that we can do to open up our possibilities is use the complement. So you're making a random guess on a 5-question multiple choice test where each question has 4 options A, B, C, and D. Is the probability of getting exactly 3 questions correct 1/4 times 1/4 times 1/4 times 3/4 times 3/4? I don't even want anybody to think about it. The answer to this question is no, but it's very easy to lead yourself into temptation and say, hey, yeah, that makes sense, because you are getting 3 questions correct and 2 questions incorrect. But this doesn't take into account that there's more than one way to get 2 questions correct. So this example here only has the person getting the last 2 questions correct. If we take a look at this in a little bit more detail, what we'll find is that there are 10 ways to get 3 questions correct. So the way that I looked at this is, and you can do this with a tree diagram, I really don't think that it would be efficient, but if you just need to be able to follow along, you don't have to make a sample space that's this big. So the way I looked at this is I'm going to get 3 questions correct. I'm going to get the first 3 correct, and then move the last question correct over 1 while keeping the first 2 fixed to correct. And so then I continually moved out my corrects until eventually I got all of the possible ways I can get 3 correct, getting the first 1 correct. And so then this continues, and what you'll find is that there are 10 different ways that you can get 3 questions correct. So while the last question was leading you into a trap, this question probably works the way that you might think it does. So there's 10 different ways to get 3 questions correct. So if we multiplied the previous probability by 10, is that the right answer? And it is, because this is now taking into account all of the different ways that you can get 3 questions correct. So this is an 8.8% chance that you get 3 questions correct. This isn't very good. But what happens if there's 10 questions? What if there's more than 2 outcomes? How can we keep on doing this if the problem is larger and larger? So actually in the second part of this unit, when we talk about the binomial distribution, that's going to solve most of our problems all in one shebang. But for now, we're going to take our all or nothing and combine the complement with this. And what we can do with that is we can end up finding just a few more probabilities by hand. That is in a similar way that we have been doing it without having to look at that sample space that we did in the previous slide. So it's pretty handy, but it's again a very visual concept, the complement is. So I recommend as much as possible you draw a picture along with the examples we do. So the first thing is understanding the complement. We've talked about it before, but we didn't really practice it very much. So state the complement of the following. In a 10-question multiple choice test, you get exactly 7 questions correct. Well, thinking about it as the opposite is kind of dangerous. What I recommend is thinking about it as everything else. So these are all of the options that can happen. You sit down and you take the test and you repeat this until every single possibility has happened. You can get them all wrong, so you can get 0 questions correct. If you took it another time, or this is an alternate universe, if you took it again, you would get one of your possibilities is getting exactly 1 out of 10 correct. So these are all of the different outcomes that can happen when you take this multiple choice test. So the complement of getting 7 questions correct is getting everything else. So that's 0, 1, 2, 3, 4, 5, 6, 8, 9, or 10 correct. So everything else besides getting 7 questions correct is the complement for this event. In a 10-question multiple choice test, you get at least 7 questions correct. So from here on out for the rest of this unit, language is going to be a very important part. There's going to be at least, at most, fewer, greater, and those 4 things are usually something that you have to think about. They don't always do what you think they would do with your initial instinct. So at least 7 means 7 is the minimum. So if somebody owes you money, they owe you $100, and you say, hey, you need to give me at least 20, then that means 20 is okay, but anything higher than that is okay too. So at least 7 correct means 7, 8, 9, or 10, and the complement of this is everything else. So that's 0, 1, 2, 3, 5, 2, 3, 4, 5, or 6. In a 10-question multiple choice test, you get at most 4 questions correct. So if you're having a party and you say, hey, to your friend, I can only have, at most 20 people over, because any more than that, it's too crowded. So 20 people would be okay, but anything less than that is meeting your requirements. So at most 4 is 0, 1, 2, 3, or 4, which means that everything else is 5 through 10. I don't know what happened to that. So 0 through 4, the only other things that you can do is get 5 through 10 correct. So there are a few more here. We haven't quite reached the complement yet, but we're close. So in a 10-question multiple choice test, you get fewer than 4 questions correct. So fewer than 4 means less than 4. So that's going to be 0, 1, 2, or 3. The complement is going to be everything else. So be careful, just because the 4 is there doesn't mean that it's included. Again, language is going to be something that is going to be something you'll have to think about a little bit more detail. In a 10-question multiple choice test, you get at least 1 question correct. So at least 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10, which is a pretty long string of events here. But the complement would be that we get 0 correct. In a 10-question multiple choice test, you get at most 9 questions correct. That's going to be 0 through 9, which means the only thing that's left here is getting 100, getting all 10 correct. Now, what you might notice is that the rest of the complements had, things that are all over the place, but we had a nothing here with getting 0 correct, and we had an all with getting 10 correct. So this is a lead-in to how the complement allows us to take our regular probabilities and find more with them without doing some crazy sample space stuff. So boiling that down, the complement didn't help us at all for the first 4 of those. However, with the last 2, when we had at least 1, or at most 1 less than your maximum, we were able to get it to a probability that we could find. So I could find the probability of getting all of the questions wrong. I could find the probability of getting all of the questions correct. But anything in between there is going to be pretty wild, especially if there's more than one part of the event to find. Let's look at an example. So the probability of a randomly selected car crashing during a year is 0.0480. based on data from the Statistical Abstract of the United States. If a family has 4 cars, probability of an accident for one of the cars is 0.0480. Find the probability that at least one of them has a car crash during the year. So this is the case where we can use the complement to end up finding something that we kind of shouldn't originally. So at least one is 1, 2, 3, or 4. So the only other thing that we have from that is 0. So if you remember, a probability and its complement add to 1. So if you were to find this probability by hand the nasty way, and then do 1 minus that, you'll get the same exact probability. So instead of doing the really gross long one, we can use the complement instead. So for a while, I'm going to suggest that you just memorize where the complement is used, because the further we go along, the more it will be able for you to understand. So I know I can find the probability that 0 get into an accident because they either get into an accident or they do not. So this would be 1 minus 0.0480. So this is going to be for each person, there's 4.9520 times 0.9520. And then we're taking 1 minus this multiplication here. If you want to use an exponent, which I definitely think is handy, you can write it as 1 minus 0.9520 to the 4th. And this ends up being 0.1786. So the complement applied here because anytime you have at least 1, you can do 1 minus the probability of everything else. So the probability of a randomly selected car crashing during a year is 0.0480. Again, the same example. Find the probability that all 4 cars have an accident in the next year. So this one is a plain vanilla. It's already set up as an all or nothing. So all 4 cars crashing is 0.0480, and we want that to happen for each of those people. So we're nice. We don't want any of them to get into an accident. When you put this into your calculator, however, you'll probably get this E notation here, depending on what kind of calculator you have. Be careful, because I will get a probability of 5.3 pretty frequently, but you can't have a probability that's bigger than 1. So you can't be a robot, you can't copy from your calculator without saying, hey, you know, that's probably a pretty messed up probability here. So this is the calculator's shorthand. If we convert this to scientific notation, what this is actually saying, then this is the same thing as 5.308416 times 10 to the negative 6. So what you do is you take your decimal place and you move it 6 places to the left. So if I did that here, 1, 2, 3, 4, 5, 6. So I know this is more than 4 decimal places, but it's not like 100 zeros. It's not like more than 10. So I would probably keep putting zeros until you get to the first non-zero digit. Find the probability that at most 3 cars have an accident in the next year. So the probability of at most 3 is the same as 1 minus the probability of all 4, because these 2 together are all the possible outcomes. So this is 0, 1, 2, and 3, and this is all 4. So we're going to make all 4 of these get into an accident, so that will be 0.048 to the 4th, and then we want to do 1 minus that. I did choose to call this 0.99999 to have 5 digits instead of rounding to 4. This would round up to 1, which makes it seem basically, probable that they would get into an accident, but it's not. So an extra digit is still better than rounding to 4, just to stick with the rule. So what can you think of about the probabilities we found so far that may be unreliable for this family? So this is when you want to think about the practical aspects of this. And what I would like to think is these people are all in the same family. So what might they have in common? So they might have similar driving habits. So maybe it's, two parents and two kids. The kids saw the parents driving their whole lives, and then they started driving. This is really similar to the example with the eggs at the supermarket. There was a bunch of cartons with broken eggs together, and it's because they all, had similar travel habits. So this again, we talked about with the teenagers getting STDs. You have to consider that they are randomly selected in order for these probabilities to hold true. So we got one more example on this. The complement is a pretty, it's a concept that is best visualized. So we can go into this topic really deeply, but we're going to kind of brush over it and just remember that anytime you have at least one, you're going to do 1 minus 0, and anytime you have 1 minus the sample size, you're going to do 1 minus the probability of all. So according to the FBI, 24.9% of robberies are cleared with arrests. So this is the same information that we saw in a previous topic. A new detective is assigned to 10 different robberies. What is the probability that the detective clears all 10 robberies with arrests? So this is already an all situation. We don't need to worry about anything with the complement at all. We can find this probability in a straightforward manner. So the probability that the person clears 1 is 0.249, but they're having 10 crimes, and we're going to assume that they behaved at the rate of everybody else. So we're saying, hey, if they were the average, how would they perform if they cleared all of these? Well, basically, this is, let's see, 0.00009%. So it's pretty unlikely that a person that was put on 10 robberies would clear them with arrests. What should we conclude if the detective clears all 10 robberies? Well, you can go a good direction, a positive direction, or a negative direction. The negative direction is that the detective is crooked. Maybe they set up the crime, maybe they planted evidence, or, maybe they coerced the person into a confession. Or you can go to the positive direction and you can say that the detective was either really good or really lucky. So maybe the crimes that they were handed had, a lot of evidence associated with them already. So it was a pretty straightforward bunch of crimes to clear. So definitely needs to be investigated regardless of which one of those it is. What is the probability that at least one of them is cleared with an arrest? So this is a situation where maybe this person's boss says, hey, you're a new detective on the case. I'm going to give you, your first 10 crimes, you need to clear at least one of them. So that would be a 10% rate, which for a super new agent, I don't think would be too bad. So at least one is not an all or nothing. It's definitely at least one is 1 or 2 or 3 or 4 all the way up to clearing all 10 of them. So we would use the complement here. This is going to be the probability that at least one is cleared with an arrest, which is equal to the probability of 1 minus the probability that 0 are cleared with an arrest. So the complement, so you kind of double complement here. The complement of 24.9% is 75.1. So we want none of them to be cleared. So we want this person to not clear the first one and the second one and their third one and so on. So this is going to be 1 minus 0.751 to the 10th, which is 0.9429. I definitely recommend going through these questions without having the PowerPoint answers in front of you. Please feel free to email me if you have any questions.